We will continue with our discussion of the TCP packet structure. Last class we have discussed some of the fields. Today we will continue to discuss some of the remaining fields. This was the TCP packet structure which we saw in the last class, and in the last class we discussed certain fields. If you remember, we discussed about source port, we discussed about destination port, we discussed about header length, we discussed about checksum, and very specifically we discussed about sequence number and acknowledgement number. We saw how TCP utilizes these two fields, sequence number and acknowledgement number, in their reliable data transfer service. Today we'll discuss about these 6 fields. There are 6 flags in the TCP header, 1 bit flags. They have the value of either 1 or 0. That means they, in certain circumstances they are set, and in certain circumstances they are kept off. When they are set, they have the value of 1. When they are off, they have the value of 0. Today we'll see the role of these particular flags, and very specifically some of these flags have very important role in the TCP connection establishment and TCP connection termination. First we'll discuss about the role of those flags which plays the role in TCP connection establishment. So first note these two particular fields about which we'll discuss today. This field, this particular flag, written as SYN, it stands for synchronization, and another flag ACK, and this stands for acknowledgement. So we'll see the role of these two flags and how they are used in the TCP connection establishment phase. Last class we briefly mentioned about the TCP connection establishment, a handshaking phase that takes place before actual transmission of data. Remember, before actual data transmission takes place, a handshaking process takes place between the two sides. Now this connection establishment phase is very popularly known as TCP three-way handshake. Why three-way handshake? Because there are 3 specific packets that are sent between these two nodes, and that's why this is known as three-way handshake. We'll see the actual process today. Now this connection establishment phase happens before sending any application layer data. That means whenever data comes from the application layer to the transport layer, before actually sending those data using TCP to the other side, a handshaking phase takes place using this three-way handshake, and after this connection establishment happens, only after that actual data transmission happens. Now let's see this connection establishment phase, how it is performed. So let us discuss the process. So let's see how the TCP handshaking takes place, how the TCP connection is established. Let's assume that machine A wants to establish a TCP connection with B. That means A wants to send certain data to B. So before sending the data, it will first establish the TCP connection using the TCP three-way handshaking. So let's see the first step. What is the very first step of the TCP handshaking phase? In the very first step, A will create a special packet. Special packet in the sense that it's a specific packet to create the connection. It does not contain any data. It does not contain any data. Obviously, data transmission will take place after the TCP connection establishment phase. So A will create a special packet. Now what is the very special fact about this packet? The special fact about this packet is that the SYN flag, the SYN flag, is set for this particular packet. This is one specific case where this particular flag is set. So SYN flag is set to 1 for this particular packet. Apart from this, A will create a random initial sequence number. Now this is also very important. A will generate a random number that it will use as the initial sequence number. Okay, so A will create a random initial sequence number and insert this number at the sequence number field. Remember, we have seen the sequence number field in the packet. So A will insert this random number in that particular field. Why this is random, we'll see later on. So this is the first step. The first step is I will create a special packet. There is no data in the packet. The SYN flag will be set. That means the SYN flag will have a value of 1, and A will create a or generate a random initial sequence number, and it will insert this random sequence number at the sequence number field. Clear? This packet is known as SYN packet. This packet is popularly known as the SYN packet. Clear? Now A will send this packet. A sends this packet to B. So this is the first step. Clear? Let's take a specific example. Say A generates a random sequence number. Let's take any sequence number, say 4500. So A generates a sequence initial random sequence number 4500. Now what will be the structure of this particular packet, this first packet? The structure is very simple. Let's see how this packet will look like. This packet looks something like this. Now I have removed those fields which are not very important for this packet. Like we do not have data in this packet, so I have removed this data field. This field is not important, this field is not important, so I have removed those fields. Now source port number will be there, whatever port A is using, and the destination port will be there. B is a web server, it will contain the binary value of 80. Now what is the specific about this packet? That this flag, SYN flag, will be set to 1. All the other flags will be having a value of 0. So SYN flag will have a value of 1 for this very first packet of the handshaking phase. Apart from this value, remember we have assumed that it uses an initial sequence number of 4500. It can be any random number. So in this sequence number field, it will insert this value. This is a 30-bit representation of 4500. So this value it will insert into this field, the sequence number field. Now this is the first packet, the first SYN packet. Now it will send this packet to B. Now let's see the second step. Once B receives this packet, assuming that everything is fine, B receives this packet. Now in the second step, once B receives this packet, let's see what B will do. B will also create a special packet. Clear? B will also create a special packet. Now what will be the very specific case in this packet? In this packet also SYN flag will be set. That means the SYN value will be set to 1. Now these are only two cases where the SYN flag will be set. Other than these two cases, for any packet SYN flag will be 0. So only the first SYN packet and this next second packet that B is creating, here SYN value will be 0. Next what B will do is B will increment A's initial random sequence number by 1. Clear? B will increment the value it has received in the sequence number field from A. So if A has sent a value of say 4500, it will increment by 1. It will be 4501 now. Now this incremented value is inserted in the acknowledgement field. Clear? Sequence number field, the next was acknowledgement number field. So whatever sequence number, initial sequence number B has received from A, it will increment it by 1 and then insert that number in the acknowledgement number field. Next, it will set the ACK flag also. That means the ACK value, the flag value will be 1. Remember there was a ACK flag there. So ACK flag will also be set as 1. This packet, because it is SYN is also set as 1, ACK is also set as 1. That's why this packet is popularly known as SYN packet. This packet is popularly known as SYN ACK packet. What are the steps of this packet? B receives the packet, it increments the sequence number it has received from A by 1 and insert this number to the acknowledgement number field. It sets the SYN flag as 1, it sets the ACK flag. Apart from this, B will also generate its own random sequence number. Now remember, data will go from B to A also. So if B is a web server, it will send its web pages. So basically, it's transmitting data. So it has to also use sequence numbers. So B will also generate its own sequence number. This is independent from A. So B will, by its own logic, generates its own random sequence number and insert this number in the sequence number field. Clear? So this is about the packet that B creates. Once this packet is created, B will send this packet to A. Apart from this, B also takes certain steps. What B does is, B allocates buffers and variables at its side. That means now B is ready for this TCP connection. So it receives the first SYN packet from A. If everything is correct, if B is capable of listening to the request of A, that means B is ready to establish the TCP connection that is A is requesting. What it will do, it will also create a special packet. It will increment A's sequence number by 1 and insert it into the acknowledgement field number. It will create its own random sequence number and insert it in the sequence field number. It will set SYN flag and it will set ACK flag. Apart from that, it will allocate the TCP buffers and variables at its size. Remember, why do we require these buffers and variables? To provide those services relating to reliability. Remember, there is something called transmission, retransmission. So to retransmit a packet, or it has to store the packets as coming from the other side out of order. For all those things, it requires buffers. Apart from this, it requires variables for specific tasks. For example, say we talked about the timer. So how it will manage a timer? Obviously, it will use certain variables to implement a timer. So it will allocate buffers and variables at its side. Now this second packet is created, this SYN ACK packet is created, and this packet will be sent to A. So B will now send this packet to A. This finishes the second step. So for example, say B creates his own sequence number 6000. Clear? Now let's see what will be the structure of this reply packet. The first packet is already received from A. Now what will be the structure of this second packet that it is sending to A? So this is a packet which B creates. See the first step here. It has set the SYN flag and it has also set the ACK flag. Though these two flags are set for this packet. Now it has incremented by 1 the sequence number it has received from A and it puts in the acknowledgement field. This is the acknowledgement number field. If you remember, if you look back, this sequence number it has received from A, it increments it by 1, so it adds 1, and whatever the value is, it inserts it in this field, this sequence number field. Sorry, the acknowledgement number field. Clear? Now it also generates its own sequence number. So we have assumed that it generates the sequence number 6000. So this is the binary value of 6000. The 32-bit binary represents of 6000. Now it inserts this number in the sequence number field. So this creates the SYN ACK flag, a SYN ACK packet which it has created. Now this packet, SYN ACK packet, will be sent from B to A. Clear the whole thing? What does this packet contain apart from the source port number, destination port number, and these other things? It creates its own sequence number which it enters in the sequence number field. It increments by 1 the sequence number it has received from A and it inserts in the acknowledgement number field, and it sets the ACK flag and the SYN flag. So this is the second packet that is created in this process, and this packet goes from B to A. Now let's come to the last and final step, the third step. So once A receives this SYN-ACK packet, what it will do? It means that A has received the agreement from B that B is now agreeing to establish the TCP connection. So now once it receives this SYN-ACK flag, A knows that B is set for this TCP connection. So what A will do is A will allocate its TCP buffers and variables. Now A will create one more packet. A will create one more packet. This packet is basically an acknowledgement for the last packet which is received from B. In this case, in this packet, SYN will be off. Here in this packet, SYN will be off. SYN flag is basically for the initial establishment, initial message. So in this third acknowledgement, SYN will be off. ACK will be set. The ACK value will be set. A will increment the initial sequence number received from B by 1 and insert in the acknowledgement field. The same thing B did in the last step, A will do this time. What it will do? The sequence number it has received from B, it will increment by 1 and it insert in the acknowledgement number field. Now A will send this ACK packet. This packet is popularly known as ACK packet. A will send this ACK packet to B. Now this finishes the TCP connection establishment phase. Once B receives this third packet, the connection establishment phase is over. Clear? After this, the actual data transmission can take place between A to B. TCP also allows A to start sending data from this third packet itself. In fact, if A wants, it can start sending data from this third step also. But normally what happens is data transmission actually starts after these three steps are over. So these three steps will establish a TCP connection between A and B, and once this handshaking phase is over, the actual data transmission now can take place between A and B. This is another example pictorially shown. So again, look at it. So this sender wants to establish a TCP connection with this receiver. So this is the first packet, initial SYN packet, where SYN is set as 1 and it uses its own initial sequence number. Say in this example, this is 521. B, after some time, the receiver receives this packet. It creates the next packet where SYN flag is 1 and ACK flag is 1. It increments this number 5 to 1 by 1, it becomes 522. This is inserted in the acknowledgement number field, and then it generates its own sequence number. So say the sequence number is 2000. So now it sends this packet to the original sender. Now after it receives this packet, it creates a third packet. In this packet, it increments this acknowledgement number by 1, 2000 by 1, so it becomes 2001. It also sets this value ACK by 1. The SYN flag is set here as 0 and it sends this packet to the receiver. After this phase is over, the data transfer phase starts. Both sides can transmit data to each other. Remember, the receiver side creates its buffers and variables in this step number 2, and the sender side, the original side which initiated the connection, it creates its own TCP buffers and variables at this step number 3. So this is a pictorial representation of this. So you see, this side now wants to end this connection. So it sends a packet with the flag set. Okay, this packet comes from this side to this side, and once this side receives this packet, it will send an acknowledgement. Clear? Now when this side is over, which is data transmission, it will send a FIN flag packet here, and this side will send the ACK packet here. So once these 4 steps are over, the TCP connection is closed. Now both sides can deallocate the buffer. When just mentioned that some of these steps can be combined, which part can be combined? This part can be combined, these two parts. That means this side sends an FIN flag packet here. This side, whenever it is sending an acknowledgement for this particular packet, this packet where FIN flag was set, it can send its own FIN flag set. So these two parts can be combined. But anyway, the termination has to be requested from both the ends. Clear? So this is how a TCP connection is closed. One important fact to note here is that say this side is now over with its data transmission, so it sends this packet where FIN flag is set. Now when this side receives this packet and its acknowledgement, this does not mean that this side has to close it immediately. It is still possible that this side still has some data to send to the other side. The side that sends the termination request means that this side is over with its data transmission. It does not automatically means that the other side is also over with its data transmission. That means the other side still may have some data to send. So whenever one side sends the request for data termination, that means that no more data is there to be sent from this side to the other side. But if some data is there to come from the other side, it's still received. Be very clear about it. That means once it sends a request for closing the connection, this means that there is no further data to be sent from this side to the other side, but if more data is there to be received from the other side, it should be able to receive. That means once it decides to close its data, it closes its sending socket, but the receiving socket is there. It is there to receive data from the other side. Only when this other side is also over with its data transmission, then only it stops it closes the receiving socket. That means it is not that the both side closes its connection simultaneously. Whenever one has its data transmission over, it can close its sending side, but the receiving side it should keep open until and unless the other side also closes the connection. So once both of the sides closes the connection, the TCP connection is completely closed. So we have discussed about these three flags: ACK flag, SON flag, and AFIN flag. The role of these three flags is very important in two important parts: the TCP Connection Establishment part and TCP Connection Termination part, which are important aspects of the whole TCP process. Now we'll discuss one more flag, this RST flag. RST stands for reset. This RST flag or reset flag is used to terminate a TCP connection abruptly. Means if there is something wrong with the TCP connection, this connection has to be closed immediately or abruptly, and in that case RST flag is used. Now this is in contrast with the graceful termination using FIN. Remember the termination which we have discussed previously. Both the sides terminate the connection gracefully. The data transmission over for one side, it will send a FIN flag packet, the other side will acknowledge, the same thing will be done by the other side. So it is a very graceful termination. But say something happens, something faulty happens in between the transmission or at the beginning of transmission. So if such a fault occurs, the connection has to be abruptly discontinued. That means it has to be discontinued then and there itself. In that case, this particular flag is used, RST flag. The side that wants to abruptly terminate the connection, it has to inform the other side that I am closing this connection. Then it will send a packet, and in that packet this particular flag, RST flag, will be set. That means say A and B is trying to start a TCP communication, but B wants to close it due to certain reasons. So B will create a packet and then it will send that packet to A where RST flag is 1. So this abrupt termination can happen at the beginning where TCP connection establishment is tried to be created, or it can happen in between data transmission. So it can happen anytime. Whenever some fault occurs, one of the side will initiate this abrupt termination and inform the other side. Now there are some 10 possible reasons where this RST flag may be used, where abrupt termination may be required. For example, say this first case, look at this first case. The packet is an initial SON packet trying to establish a connection to a server port on which no process is listening. So what does it mean? Say A is sending a request to B to establish a TCP connection. So it sends a SON packet, and this packet is sent to port number say 80. Clear? So say A wants to create a TCP connection to B. So what is the first packet? The first packet is a SON packet. Now say this packet is sent to port number 80. Now say B is not listening on port number 80. It is not a web server. It is something, a file transfer server. It is not listening on port number 80. The port number 80 is closed. But a SON packet has arrived at B. Now what will B do? It is not listening on port number 80. So it will simply, when this A has sent a SON packet, it will send simply a reply where the RST flag is set. That means I cannot accept your request. So it disconnect whatever request has come from A. Another reason is that the packet arrives on a TCP connection that was previously established, but the local application already closed its socket. That means say A and B has established a connection and now data transmission is going on, and for some reasons, due to default at the other side, or due to OS, the operating system of the other side, closing the receiving socket, the application has closed. Now A's packet is coming. Now B has received those packets, but the application which was taking those packets is closed now due to certain reasons. Now what we will do, because the packets are now cannot be delivered to that application because the application is closed. So what we will do, we will send an RST packet to A. That means it will create a packet where RST field will be set to 1 and it will send to A, saying that now this connection has to be closed because something fault has occurred at my site. Clear? There is another reason why this particular flag is used. It is used for in cases where there are actually certain malicious behavior. Someone tries to hijacking a TCP connection, and if that site, that firewall of that site recognize that someone is trying to maliciously attack that site, it resets the connection immediately. So these are some of the possible reasons where the TCP connection has to be closed abruptly. Clear? There are other circumstances are also possible, but very rare. These are the three most possible cases where the termination has to be closed abruptly, and to close a connection abruptly, this particular flag, RST flag, is used. Clear? So we have discussed this particular flag also, RST. Now we are left with two flags, URG and PSH. Now let's discuss this flag called URG or urgent flag. Now you know what's the meaning of urgent. Now look at the process, how actually the data is delivered to the application layer. Say A is sending data to B. Clear? A connection is already established between A and B, and A is sending data to B. So packets are going from A to B, one after another. Now it is not like that once one packet arrives at B and B will send that packet to application layer, the other packet arrives, it will send the packet to application layer. It is not like that. Once a packet arrives, it is not like that it will send the packet immediately to application layer. What the receiver end does is it buffers the packet. It buffers the packet. Sometimes packets are out of order. It has to buffer those things. Obviously, it has to buffer those things to make them in order. But again, if packets are coming in order also, it does not send this packet to the application layer one by one. It does not send it immediately. What it does is store these packets in a buffer. Say B has a TCP buffer. So packets are coming. Once the buffer is full, then we will send a good number of packets to the application layer. Why does it do like that? It's because for the operating systems, you all know what is context switching and all these things. Because if I have to send each packet individually, I have to inform the operating system. I have to invoke the necessary services every time a packet arrives. So this creates a lot of difficulties for the operating system. So what the receiver does is it basically buffers a number of packets, and once the buffer is full, it transmits those packets to the upper layer, the application layer. Now because of this behavior, says there is a packet which is urgent. Now this packet has to be delivered immediately. Now normally what we'll do, once this packet arrives at B, we will buffer the packet. Once the buffer is full, then it will deliver this packet to the application layer. But there is a packet where there is some urgent data. Now this data has to be transmitted immediately. So in this case, this particular flag is used. Whatever packet contains urgent data, in that packet this particular flag has to be set. URG has to be set as 1. Clear? Once the other side receives a packet where this particular flag is set, what it will do, it will understand that this packet contains urgent data, and then it will send this packet to the application layer on a separate channel. Now, what's the meaning of separate channel? Now let's understand with an example. Say you have a factory where you have a gate, and trucks are coming in line. So the trucks are bringing some materials. So the first truck that is coming will enter first, the next truck will arrive next, the third truck will arrive next. They're coming in order. Now say one truck has arrived with a red flag. Now say when someone has a red flag, it means it contains some very important material. That means that particular truck has to be allowed to enter in the factory immediately. Now because the trucks are coming in line, that's why that particular truck has to be taken through a separate gate. So you open a different gate and ask that particular truck which is carrying a red flag that you come through this gate, because it understands that that particular truck is carrying some very urgent material, so it takes the truck through a different gate. The other trucks are coming in sequence by the normal gate. Same way, if a packet arrives with the URG flag set, it means that this packet contains urgent data. So what the receiver side will do, it will deliver this packet to this application layer through a separate channel. Now this is again very rarely used. It's a very rarely used flag. It's only in special circumstances where this flag is used to send some urgent data, some urgent signal. If required to be sent, then this particular flag is used. Now whenever our URG flag is set, it has to be used in conjunction with this urgent data pointer. That means whenever this flag is set, whenever a packet contains urgent data, this particular field is also used, urgent data pointer. What does it mean? That means this packet contains urgent data, and this urgent data pointer will point to which amount of data is urgent. That means it is not necessary that the whole data is urgent. That means say I have 50 bytes of data. 50 bytes of data in my data part. Now it is not necessary that all the 50 bytes are urgent data. Clear? So this urgent data pointer will point to which amount of data is actually urgent. Clear? So whatever value is there in the urgent pointer field, this value will help to identify the other side which amount of data is actually urgent. Now this is the actual formula. So the number of urgent bytes is given by the urgent pointer value plus 1. That means say if this value is 10, say this value is 10, that means 10 plus 1, 11 bytes of data starting from the beginning is urgent. There are 50 bytes of data. Out of these 50 bytes, the first 11 bytes are urgent. That means whatever value is there in the urgent data pointer field, that means that is incremented by 1, and that amount of data is urgent in that particular packet. This particular formula also works. They are basically the same thing. This indicates where the urgent byte ends. The same thing can be used. So this also indicate where the urgent data ends. So this is given by end of urgent byte is equal to sequence number of first byte in the segment plus urgent pointer. What does it mean? That means say the sequence number of this packet is say something like 20. The sequence sequence number of this packet is 20. What does this mean? That means the first number of the first byte is 20. I hope you remember this. This was discussed in the last lecture where we discussed sequence numbers. So sequence number indicates the number of the first byte. So 20 is the first byte. So if I add 20 with the urgent pointer, 20 plus 10 is 30. 20 plus 10 is 30. That is up till 30th number byte we have urgent data. That means byte number 20, byte number 21, byte number 22, byte number 23, 24, 25, 26, 27, 28, 29, 30. So up till byte number 30 I have urgent data. So this also calculates the end of urgent byte. Now if you look at it, they both indicate the same thing. So I can directly say whatever the urgent data pointer is, this plus 1 is where this is the total urgent data, and also if I add to the this sequence number to this urgent data pointer field, it will indicate where my urgent data ends. So basically they are same thing. So I guess you have understood how this particular field is used, and remember this particular field URG flag has to be used with this urgent data pointer, and again this particular URG flag is very rarely used. It is used only where there is a requirement of sending very urgent data. Clear? One more flag which is remaining, we'll discuss. This is the PSH flag. Now whenever this PSH flag is set, it means that all the segments in the receiver buffer are to be immediately pushed to the receiving application. Again, go back how these two sides work. So A and B are connected and data is being transmitted from A to B. What B does is it buffers the packets in a buffer, and once the buffer is full, it delivers this buffer to the application layer. Then it will continue receiving packets. Then again, once it is full, it will again deliver to the application layer. Now if a packet arrives where PSH is set, whenever PSH is set, it means that do not buffer packets anymore. Do not buffer packets. Immediately empty the buffer. Empty the buffer immediately. Whatever packets were there and this packet that has arrived, immediately deliver the packets to the application layer without waiting for this buffer to fill up. Why does it do something like that? This is done because A understand that the B side B, we will wait for this buffer to fill up. Now say if A has some important data and it wants that the data has to be sent to the other side as early as possible without waiting for the buffer to be filled up, it will create a packet where this PSH flag will be set. So once this packet arrives at the other end, if it receives a packet which PSH flag is set, what it will do, it will empty the buffer immediately without waiting for the buffer to fill up. Now remember, PSH does not mean that this particular packet has to be sent immediately to the other end. It's not like the flag where URG flag was set. Whenever URG flag was set, that packet has to be sent immediately to the upper layer through a difference channel. But whenever a packet arrives with a PSH flag is set, it means that now do not buffer. Already buffered packets are sent in order. Remember, the packet with the PSH flag set is not given any preference. These packets will be delivered to the upper layer in order. So the packets that were buffered before will be first sent, and this particular packet with this PSH flag set will be sent to the upper layer accordingly. But the only thing is that the packets will not be buffered, they will be immediately sent to the upper layer. Subsequently, once this buffer is free, what next packets that are coming from A will again be buffered in this side. Clear? Now again, this it is normally, it's not preferred that any side uses this particular flag, PSH flag, because this create problems with the operating system. So in the actual practical TCP, you will rarely find a case where this particular flag is used. Okay? So PSH flag, like URG flag, this is again used very rarely, in rare circumstances. So today we have discussed these six flags, and then also we have discussed about this urgent data pointer, which is related to this particular flag URG. Now this flag receive window, this we will discuss in a separate lecture. Because this particular header field is used to provide a specific TCP service known as flow control. A very specific service of TCP. Flow control is achieved using this particular header field, so we will discuss it in a separate lecture. Let us also very briefly discuss about something known as SOIN flood attack. Now this is a type of denial of service attack. You must be knowing what a denial of service attack is. You might have read some news about denial of service attack against certain website. This sort of news they frequently appear. Now, denial of service attack is something like this. Say this is a website and you want to take the service of this website, you want to access something from this website, and suddenly you are not capable of getting the service because some of the attackers have done such an attack that this service becomes unavailable to people who want to access it. So this is known as a denial of service. You do not get the service. The service is denied, but this is done maliciously. It is not by any technical fault, it is done maliciously. Now, why we want to discuss this? Because the first denial of service case that was documented was done using this particular attack known as SYN flood attack. So the first documented denial of service attack was done using the SYN packets of TCP. So you should actually know how this was done. Though there has been people have found ways to avoid this, but you should understand that there is a particular drawback of the TCP connection establishment phase, which can make people, cyber criminals, create this type of attack on a particular service. Now let's see how this denial of service attack is done using this SYN flood attack. Now let's understand this way. Say B is a website and it is listening on port number 80. Okay, and now some of the organized cyber attackers or cyber criminals want to mount a denial of service attack on this particular website so that people are not able to take this service. Now look at the way TCP connection establishment takes place. A client sends a SYN packet to this server. I'm talking about the three-way handshake. The first packet with this SYN flag set as 1. Okay, so this first packet is sent. When this packet is sent to B and a B is capable of providing a request, what it will do? It will send a SYN ACK packet. It will also allocate the buffers and variables when it's sending this packet, and then the third packet arrives, the ACK packet, and then the TCP connection establishment takes place. Now look at this point. This point is important in this attack. These buffers, these TCP buffers are created by B whenever it receives a SYN packet from A. Clear? That means as soon as it receives a request for TCP connection establishment, if it can accede to the request, if it is capable of granting that request, then it will allocate it buffers and then it will send the reply to A. Now what happened in this type of attack is that many of cyber criminals came together. They coordinated at the beginning that we will mount an attack on this web server, say at a particular time. So at this particular specific time, they all sent a request at SYN packet to this particular web server. So many servers coordinated and many machines coordinate among themselves and they send an SYN packet to this particular web server. Now every time it receives a SYN packet, it will allocate buffers. Now if it receives a lot of SYN packets almost simultaneously, what will happen? It will create buffers for every one of these requests. Now if a huge number of such coordinated requests comes and it will go on creating buffers, TCP buffers for each of these requests, it may happen that the amount of TCP buffers created will swamp this server. Now say around 5,000 cyber criminals coordinated on sending this SYN packet to this site. Now everyone will be sending this request packet. It will create buffers, and then because of these buffers, the capability of server will go down. Now what happened? It sends a reply, and the other side does not send this ACK packet. That means of the three-way handshake, the third message is not sent by that criminal. What it does is send a SON packet, the other side, the server side, allocates the buffer, send an acknowledgement packet. It is not supposed to send the third packet, but it withdrew. It did not send the third packet. It kept it that way. That means the buffers are allocated there. Like that, many of the criminals coordinated together, and because of so many buffers being created, some actual person who want to access the site is not capable of accessing the site because the buffers are full. There is no space to create any more buffers. So this is an example of the first denial of service that was mounted using this type of attack. This particular attack is known as SON flood attack. So this was just an information about how this drawback of TCP connection establishment can cause a denial of service attack. Clear? So that's it for today. So today we have discussed those 6 flags, the urgent pointer field, and then we also talked briefly about denial of service attack mounted by a drawback of the TCP connection establishment phase. Next class we'll discuss about TCP flow control, which is achieved using the TCP and the window size, that particular window size field. Till then, goodbye.